I'd like to invite Daniele forward. I'm not going to give an introduction for Daniele because in his words, it has been covered. So he'll take the second part of the session, so the quantum field theory of space-time, and he can take the floor once the microphone is connected.
I also wanted to participate in this rushing through your talk competition. Is a new challenge because you normally do it only in the last 5-10 minutes of your talk, but I'll do it from the very beginning, although we already have a winner. So I also feel much more, I feel more relaxed. Anyway, so I try to understand what the organizers meant by quantum field theory of space-time, not because I have no idea about that, but because, first of all, that is supposed to mean that space-time is fully dynamical. And basically any non-perturbative theory of quantum gravity will then be, according to this understanding, a quantum field theory of space-time. So I guess that maybe they had in mind something else, because all the rest of the conference has been already about quantum field theories in one form or the other of space-time. So this is a quantum field theory of space-time in the form of a path integral. So maybe I thought that they were referring to topology change, to topology being also dynamical, because that's the thing that in a path integral definition of quantum gravity, it stays fixed a priori, just as it stays fixed in classical GR, in the form of the action. So that's how I interpret the story. But then I also thought that they could mean maybe unconsciously something else, which is that you may want a quantum field theory of space-time, which is also looking familiar. Maybe you want to do perturbation theory, but you're still at the level of full non-perturbative quantum gravity one way or the other. So topology change, and also some sort of standard quantum field theory formalism, maybe using a background, because that's how we are normally using quantum field theory. So I interpret again the story as being a quantum field theory with topology change on some background. And that background can only be some background structure which is there in full GR. Because we want background independence in the same sense of GR, at least. So the available backgrounds would be the topology again, but we already said that it cannot be the space-time topology according to the first part. Then it could be, this background can be the space of geometries, so-called superspace, the configuration space of our geometric and matter fields. It could be the signature, it could be the local gauge group of gravity that is the Lorentz group. These are allowed background structure because they're already there as background structure in full GR. Okay, spatial topology constituents in the spirit of the emergent space-time ideas that Baylock has discussed in his space-time and geometry would emerge as some collective notion. And I just want to emphasize that this applies to flat space-time as well. We are not talking about curvature only being emergent. It's the full space-time notions that are emergent. So flat space in this picture is itself a highly collective, non-perturbative, approximate, reconstructed object. Okay, so it has to be a quantum field theory with standard, more or less, QFT language on some of those background structures, possibly in the spirit of emergent space-time, and a quantum field theory with topology change, spatial topology change, and therefore dynamical space-time topology. On one of those backgrounds, superspace has been proposed a long time ago by many people, some of which are in the room. This is ruining all my rushing thing. Which I was already on the losing side. Oh, that's worse. Okay. So I'll keep rushing also through this thing. So you have heard from Klaus on the very first day the whole story about the whole setup about canonical geometrodynamics. So that I can really rush through quickly. So you study canonical quantum gravity at classical level, then you move to the quantum level. You have a dynamics encoded in the Wheeler-DeWitt operator, the Hamiltonian constraint. And you have, if you're good, a full Hilbert space of solutions of physical states solving the constraint. You have quantum gravity on a given global hyperbolic manifold, supposed to be the full story. In fact, you can also formulate the same story through a path integral. Here I connect with what Steve was mentioning earlier. You can consider the path integral as not a solution, as defining a solution of the Hamiltonian constraint, but a green function because of causality restrictions. So it's actually an actual propagator of physical states. And that has to do with the range of the lapse integration, which becomes proper time in the appropriate gauge. And for recent work and very old work explaining how these ideas are implemented in the context of spin foams, there is those references there. Now, people maybe were voicing dissatisfaction with this simple picture, not only because, of course, we didn't manage yet, well, we don't manage yet to complete the full story, otherwise the conference would look very different. But they were mentioning that because on the indefinite signature of the supermetric, the metric on superspace, this single universe interpretation or setup may not be fully satisfactory from the quantum point of view, the quantum theory point of view. Moreover, people started suggesting that a dynamical topology could help explaining values of the parameters of our theory, in particular the near vanishing value of the cosmological constant. Before I tell you how they were doing that, then let me also mention that the path integral is more general than this definition. It can be defined, at least in principle, on arbitrary space-time topologies. And so you can consider a Pant topology with two legs and one trunk. And the path integral will define a functional of the three boundary data, the three metrics on the three boundaries, components of the boundary. Now, how you go beyond and incorporate this type of topology changing processes? Well, you promote the canonical wave function to a field on superspace, a field on the space of geometries. And then you write down an action. This is taken from the old paper by Steve and Strominger. Thanks, Steve, for not allowing me to use all the slides, because I didn't ask, but I used them anyway. So you write down a kinetic term, quadratic, in the field on superspace, with the kinetic operator being the Wheeler-DeWitt operator. And you integrate over superspace with the functional measure. So this is one higher level of mathematical formality, if you want. If you could do that, you could actually do the path integral. But here we are assuming that you can do the path integral and you want to actually incorporate also topology change. And the fun comes with the interaction term, because the interaction term is exactly what is supposed to govern the topology changing processes. It connects three fields functionals of 3 geometries on 3 universes with some matching conditions at the junction. Is the Pant topology that I mentioned earlier. Then you can write down the classical equations of motions, and these are going to be a nonlinear and non-local on superspace correction or extension of the Wheeler-de Witt equation. And this is the classical one, and then you're going to have the full quantum equations of motion with the same type of interpretation, and now incorporating all topology changing processes. That's the idea. That was the idea. And if you span, well, assuming you can write down the quantum theory and assuming you decide to expand it perturbatively, the idea is that you generate a sum of processes corresponding to all possible wormhole corrections to the global hyperbolic topology, each weighted by a Feynman amplitude, which is itself given by the path integral, the full path integral on the given topology. That was the idea. Now you can discuss the Hilbert space of this extended theory. It would either be a sort of timeless Fock space with all the possible components corresponding to universes, each with the full physical inner product of the canonical geometrodynamics theory, or you can deparameterize with respect to whatever preferred variable you find on superspace. You choose it as the time, and then you canonically quantize the whole thing with respect to that. This is a third quantized, deparameterized formulation of canonical quantum gravity in a way for all the components. Obviously, all this is extremely formal, and it would take a talk to just list all the reasons why this is formal, and we are all trying to address in one way or the other at least one of the aspects why this is formal. So people have mostly studied this in mini superspace restrictions. In the old days, in the standard geometrodynamics language, but adapted to mini superspace. More recently, we've done it in the language of loop quantum cosmology, but it's the same idea. I just want to mention that there are two possible interpretations of this mini superspace stuff. One is, is the previous story symmetry reduced? Fine, that's clear. Another possibility that is actually quite interesting, since now the thing that you're creating and annihilating are homogeneous universes, you can also reinterpret them as homogeneous patches of an otherwise single but inhomogeneous universe. This is the separate approach to cosmological, separate universe approach to cosmological perturbations. And the theories governing the merging and splitting of these patches of homogeneous, these homogeneous patches of an inhomogeneous universe. But the point is still that the classical equations of motion of such mini superspace third quantized theories will be nonlinear quantum cosmology, a nonlinear extension to quantum cosmology, because you have a Wheeler-de Witt term coming from the quadratic part of the action plus some nonlinear term. Okay, how do you go forward? You can go discrete, and we've seen that that's a very reasonable and well-explored way of trying to make sense of the path integral in itself or of canonical quantum gravity. So let's go discrete. What does that mean? It means that you chop your universe into building blocks, simplicial building blocks in one example. So the discrete path integral will have to replace the continuum one in the Feynman expansion of your third quantized theory in this discrete formulation. So it means that whatever was your path integral, your continuum one, it should actually be defined through either a sum over all possible values of discrete geometric data like the edge length or the area on a given lattice and then refined, or by summing over all triangulations taken, for example, to be equilateral, like in the dynamical triangulations approach and appropriately sent to a continuum limit. And this should apply to each of the Feynman amplitudes. Or it could be a combination of the two, which is in fact a complete definition of a spin-found model. And it could be a way to combine the lattice path integral definition. So the issue here would then be, if you start from here, somehow identify what sort of third quantized action produces this sum over discretized manifolds. But in this way of proceeding, you are trying to reproduce full lattices for your universe. Well, we don't really have examples of this except in the 2D case through some papers by Jan, for example, wherever it is. How to go forward to try to generalize to 3-4 dimensions the same idea. You can go atomic, meaning you actually not only imagine your universe as chopped into building blocks, but you try to write down a field theory for the building blocks, meaning a field theory in which the quanta of your third quantized field are actually the building blocks, these small simplices, the individual simplices which are created, annihilated to form lattices. So this is more in the spirit of the emergent space-time scenario, because then this quanta would be your candidate fundamental degrees of freedom. Well, we have examples of this and some generalizations. So the last part of the talk will be telling you about these generalizations after I told you about the example. The example is matrix models for two-dimensional Euclidean quantum gravity. And the idea there is that you write down an abstract theory of matrices, each somehow interpreted as a one-dimensional object, a segment, and in such a way that the interactions of the model correspond to 3 such one-dimensional objects forming a two-dimensional simplex. A theory like that, when you expand it in perturbative expansion in Feynman diagrams, will produce a sum over two-dimensional triangulations weighted by a purely combinatorial amplitude, depending on the size of the matrix, that's one parameter, whatever coupling constant you have, and the combinatorial structure of the diagrams, or of the triangulations dual to the diagrams. Well, so this is basically a Euclidean dynamical triangulations generated through a matrix model. And you can interpret it because you're producing diagrams and therefore triangulations of any topology, because you're gluing together triangles in not any way. This is a discrete and locally generated, so atomic, third quantization. You have a sum over discrete geometries and a sum over topologies. In this 2D case, the topologies are all wormholes. They are only characterized by the genus. There's nothing else you can say about the triangulations, about the topology of the triangulations. This you can control analytically and for anything you want to do, basically. I'm simplifying, of course. In higher dimensions, you can move from matrices to tensors, but the story is the same. Your tensor will be some simplex, maybe not one-dimensional, but two-dimensional or three-dimensional. And the abstract theory of tensors, if you choose appropriately the combinatorial pattern of interactions of the tensors in the interaction term of the action, will produce Feynman diagrams dual to simplicial complexes of arbitrary topology of the desired dimension, topological dimension. This is a scheme of combinatorics in the 3D case. Rank 3 tensors producing three-dimensional simplicial complexes. The Feynman amplitudes will be again purely combinatorial because there's no other data apart from the size of the tensor. There's no dynamical additional data that you are putting on the lattices. So it's again a purely combinatorial third quantization. This sum is again over all possible gluings of simplices, so it includes by construction any possible topology. And in fact, it's worse than in the 2D case because at least you don't get only wormholes. You get really any topology. So you have also that problem to control. Okay. Correspondence to gravity will have to be found in some continuum limit because otherwise it's a finite dimensional system. Okay, you can say this is too simple or not crazy enough, depending on your point of view. And so you add data. You add data, let's say, so that you can go more in the direction of the mini superspace at least, or the full third quantized idea for gravity, and you can recognize something like superspace and some gravitational path integral with dynamical geometric data in a more explicit fashion. So you add data and you go from tensors over a finite set to tensorial fields over smooth domains, copies of a smooth domain, and for a number of reasons it's convenient to choose a group manifold as a domain. You can in fact also add local directions, and I will discuss them in a second. So the general idea would be to have the same sort of combinatorially non-trivial pattern of gluings in the interaction term, so that the Feynman expansion will again produce Feynman diagrams dual to simplicial complexes of any topology. The combinatorial story doesn't change from tensor models. You're just having additional data. But this is now a proper quantum field theory. You have to put cutoffs and then you have to renormalize, but to start with is a field theory. So what sort of data? Well, we want to go quantum geometric because a bunch of other friends on top of the simplicial gravity and dynamical triangulations people have also learned a number of things. So let's take that into account and we try to incorporate quantum geometry. Before I do that, I just want to reassure you that a lot of work has gone into making sense of this type of models as field theories, understanding the topology, the combinatorial structures, renormalizability of these field theories, and the trade-off is always the same in physics. The simpler your model, so maybe less realistic, the less control you have at the mathematical level, and the more realistic the model becomes, the more you have to be satisfied with approximate methods or some wild guess and so on. But we are used to that. We are physicists, at least most of us, sorry. Okay, so there is a lot of work there on all this, the type of models that you can build within this type of framework. But let me move to the quantum geometric ones. I can luckily refer to you to the talk by Hal about how you quantize simplicial structures. So let's say that our building block, our quanta, are quantized tetrahedra in terms of SU2 data. Every geometric operator can be expressed in terms of quantum operators acting on a Hilbert space, and that Hilbert space is the Hilbert space of a quantum tetrahedron, which admits as a basis of spin networks with a single node. The quantum geometric data are basically the spins and the intertwiners. I've added scalar degrees of freedom that you can interpret as what you get when you discretize a scalar field, a real scalar field on the same type of tetrahedra. Some additional real number and you have the corresponding Hilbert space. And you can put there any number of scalar fields. I will use them in a second. So you can, knowing the Hilbert space of a single quantum tetrahedron, you can write down a Fock space, and you can define operators that second quantize the volume of individual tetrahedra and give you the total volume of the arbitrary number of tetrahedra, and any other geometric quantity in principle can be second quantized in terms of creation and annihilation operators. This is really boycotting my Russian thing. I'm doing my best, but I can still do it. And I refer to the other talks, to these other talks about the whole story of how this glue tetrahedra, equivalently written as spin networks, have a lot of interesting entanglement properties. Then we have the general story, which holds true here as well, about the diagrams being simplicial complexes in perturbative expansion. The new element is that the amplitudes, which of course depend on which model you are considering, there's no universal amplitude, will be functions of all the group theoretic data that you're using to describe your quantum geometry, your spin networks, your geometric eigenstates, and so on. So the general guideline for choosing interesting models is that you want your Feynman amplitudes to look like lattice gravity path integrals or equivalently spin-form models. So that you have the quanta being, as I said, spin network vertices, entangled many-body states being spin networks, and the perturbative amplitudes being spin-form amplitudes or simplicial gravity path integrals. It's a guideline for model building, not a necessity of life. Okay. Now, suppose I give you one such model. Apart from telling you this connects to loop quantum gravity, connects to spin form, so it is at least as decent candidate to quantum gravity than any of these other approaches, because it shares all of those structures with a change in perspective. You want to actually extract some gravitational dynamics. And this is an outstanding challenge for all these approaches, as it must have been clear from all the other days of the conference. Is the important challenge if you don't start from a geometry, a manifold, and so on. So the idea is that at least to look at this system as a sort of a weird quantum many-body system and look at the simplest type of collective physics you can think of, because that may have the chance of corresponding at least to the simplest type of geometric dynamics that you can consider in classical GR, that is homogeneous cosmology. And then you try to do more than that. So the idea is to try to look for the hydrodynamics of quantum gravity with this type of models. And because despite what you may think, we're modest and humble, I will answer this comment in the discussion session, because I'm still rushing. So, of course, the full effective continuum theory out of all these myriads of quanta and weird structures will be the full quantum effective action. But because we are humble, then we take the simplest approximation to that, the mean field, the classical action. Okay? We have it, and so we are just looking to the simplest form of hydrodynamics with this type of degrees of freedom, the simplest type of collective dynamics. And that means looking at super simple states which are clearly missing a lot of information. In particular, they are missing a lot of the connectivity information of spin networks and extended lattices. But they still include an infinity of spin network degrees of freedom and an infinity of simplices. So it's something that is extremely simple from the field theory point of view, but if you are trying to have that sort of approximation looking at the spin foam expansion or at the lattice path integral, it would be highly non-trivial. Still missing a lot of information, is an approximation, but non-trivial. Okay. And before I go to the final statements, I point out why two general features that are to a large extent model independent. The first one is that for quantum geometric models, so for models in which we incorporated nicely the quantum geometry of individual tetrahedra, your condensate wave function, your mean field, lives on a domain which is in fact isomorphic to the mini-superspace of homogeneous geometry. So it is mini-superspace, the continuum mini-superspace of quantum cosmology. Moreover, but this I already anticipated, once you understand the first point, once you realize the first point, well, you realize that the hydrodynamic equations are, again, the thing you've seen earlier, a nonlinear extension of a quantum cosmology equation. There's a wave function on mini-superspace satisfying some nonlinear equation. So this is what I already said. It's just that your interaction terms are not suggested by this mini-superspace interpretation or by the topology change interpretation. They are suggested by the simplicial gravity picture. So it gives you a third way of defining some nonlinear quantum cosmology-like equation. And then, okay, this is very general, but at some point you take a specific model, and we took the EPRL model parametrized because there are a number of ambiguities in the construction and we want to be a little bit more general. And then skip to the final result. So you do a procedure using in particular the extra scalar fields that we introduced at the discrete level to define for you a relational frame. You can do the whole construction assuming also isotropy to simplify the story. You extract the hydrodynamic equation and then you turn that into an equation for observables which, when written in relational form, admit the interpretation as the volume density at a given point evolving in the clock time, and a number of other relational quantities of interest for cosmology. You extract the corresponding equation, and you find at a decently general level that when the universe is small at early times, in fact early clock times, the interactions are negligible if you assume that the coupling is small, and you find something like a bounce. You find that the volume doesn't reach zero. And the mechanism is very similar. Well, the form of the equation is very similar to quantum cosmology, to loop quantum cosmology in particular. But in fact, if you look at the details of the mechanism, the origin of the bounce is different. When the universe expands, the interactions may still be negligible, and so you can still work with the free theory, and you recover a relational form of the Friedmann equation. When the universe keeps expanding, the interactions become relevant and then dominant. And that produces, under a bunch of approximations and in a more phenomenological treatment, so I don't want to claim any generality of the result, an accelerated phase. The quantum gravity interactions between the simplices push the expansion. And there are many more results that I can tell you about, but I won't. This is the summary. I will leave it here for a few seconds. And then I can in fact gain a few more seconds hoping for the kindness of the... And then I thank you for your attention.
Thank you very much. So what I suggest is that we don't take any questions, because I see many hungry faces, and we really want to start sharply with the afternoon parallel sessions. So let's thank the morning speakers as well as Bart for actually saving the morning session.